Hi everyone, this is Amruta pursuing MTech first year case in Mahindra University, Hyderabad, and today I am here to present my course project Determination of Natural Frequency of a Simply Supported Steel Beam in Structural Health Monitoring under the guidance of Dr. Visalakshi, who is an expert in structural health monitoring. So before going in detail of my course project, first of all, what is a structural health monitoring? Structural health monitoring involves the observation and analysis of a system over time using periodically sample response measurements to monitor changes to the material and geometric properties of the engineering structures such as bridges and buildings. So, what is the importance of the structural health monitoring? As we know, aging of the structure leads to the degradation of the structure and it leads to the failure. So, due to the failure of many structures, there will be a huge amount of damage to the life and property also. The structural health monitoring provides a useful tool for ensuring the integrity and safety, detecting the evaluation of the damage, and estimating the performance deterioration of the civil infrastructures. So why we should maintain the structure? What is the importance of the maintaining the structure? So as we already discussed that aging of the structure will lead to the failure of the structure, which again leads to the property loss and mainly a human loss. So to mitigate all this, to avoid all this, we should maintain the structure. But not all the structures needed the maintaining, only the few structures which are more important and valid for the economic growth of the country. So such as, for example, structures like nuclear power plants, dams, bridges, oil refineries are vital for the economic growth of the country. So they ensure the safety and security for the public life. They govern the commercial value in the market. Further, society essentially needs depends on these structures for various reasons such as economic, life quality and safety, and even employment perspective also. But unfortunately, most of the structures are also critically aging, which can result in the strength degradation, quality of the appearance, and load capacity, and overall dependency reduction. So we know that aging can lead to the degradation of the structure, whereas the society depends on these structures now to ensure and continue a comfortable dependency on the structures. Maintenance is most important. So what are the objectives of the structural health monitoring and what the structural health monitoring does? It increases the safety, detects the earlier risk, it gives the longer span of the structure and enhance the cost efficiency. So before going in detail of my course project, what is a natural frequency? So the frequency at which a system oscillates when not subjected to a continuous or repeated external force. So what is the importance of choosing this project is when an object vibrates at a frequency equivalent to its natural frequency, the vibration of the amplitude increases significantly, which could lead to the irreparable damage. Therefore, it is important to know the natural frequency. So this is the introduction of my course project. So now I am going to correlate the results from both the MATLAB and simulation work. So what I'm going to do is I'm considering a steel beam and by monitoring it and by monitoring it, I am going to take the data from it and I am going to plot the mode shapes and getting the natural frequency from the experimental work by doing in the MATLAB, and again I am going to do the simulation work in the ANSYS software by giving the same thing. So by doing these two, I am going to correlate each other and we can know how the accuracy of the both the things are. So now I am going to show my experimental work. Continuation to my introduction, I'm going to do my experimental work now. So I have considered a steel beam, which is a geometrical section of C section. Now I have considered the C section beam with a length of 750 mm, width of 62 mm and height of 30 mm. So this is my C section beam, and which I have divided the section into 5 equal parts so that I can have the more failure in the C section beam. So as we know that as I have considered my beam in a simply supported way, I have kept my C-section beam in a simply supported manner, and after that I have bonded a disk sensor to my sensor with to my beam by using a epoxy layer adhesive. By keeping the epoxy on the structure and bonding the sensor, I have connected the coaxial wires to the sensor, which is connected to the oscilloscope. So this is the oscilloscope which has collecting the data from the sensor and from the impact hammer as a input of force and output as a response. So both the data is collected from the oscilloscope. So this is the impact hammer what I have considered, and it is attached with a disc sensor here. Now I am giving a random point of hitting position. So if we consider a point randomly in a beam, so I am giving the force like this. See, now here we are getting the force and response position from the structure. So these are the input and output from the structure. So by giving like this, we are changing the positions of the structure wherever we need. So I am taking the position first position. So this is the what the response and the input what I have got from that initial position is, it is the first hitting point, and when going to the second hitting point, so this is the response and the force from the second hitting point. And similarly we are hitting the structure in third point and getting the data like this. So and for every point wherever we need, we are changing the positions of the hitting position, and we are getting the response from the same sensor. So this is the experimental work what I have done, and by this we are collecting the data from the every hitting position, and by collecting the data we are going to do analysis in the MATLAB. And at last I will compare both the experimental work and the simulation work what I have done. Thanks. Collecting the data from the experimental procedure through oscilloscope, which is force and response in an Excel file. So by inserting the Excel file into the MATLAB code, and I got the response versus time and force versus time and frequency versus FRF from the first hitting position. So uh, and this is the second hitting position, where again I got the response versus time, force versus time, and FRF versus time. So this is the data how it varies from the position, like from first position to second position, third and fourth. It's because of based on the response from the structure. So this is the third hitting position, as usual, response versus time, force versus time, and FRF versus time. This is the last one, last hitting position, that is the fourth hitting position, response versus time, force versus time, and FRF versus frequency. So here we are seeing that response versus time graph for H35, where here 3 and 5 represents, where 3 is the response what we are getting from the structure. That's nothing but the 3 is the bonding of sensor, that is sensor position, and fifth one is the hitting position. So we are hitting the we are giving the force by hitting with an impact hammer on the fifth position and getting the response from the third position where the sensor is bonded. So this for everyone, we are bonding the sensor at the mid of the beam, where it gets, as we know that simply supported has the more bending moment in the midsection. So the sensor is bonded at the mid one. So here 3 is the sensing data of the structure. So fifth one is the hitting position. So this is how I got the response versus time, force versus time, and the FRF versus frequency. So these are the data what I have collected for the every hitting position, like 4 hitting position, and these are the mode shapes what I have got from my response. So this is the mode shape 1, mode shape 2, and this is mode shape 3. So by resulting these mode shapes, I have got the natural frequency, where the first natural frequency is 192.13 Hertz, and second natural frequency is 604.23 Hertz, and third natural frequency is 1056.76 Hertz. So these are the results what I have got from the MATLAB through experimental procedure. So now I am going to correlate these results with the simulation part, which is going to be done in the ANSYS software. So by comparing these results, we can know the accuracy of both the things, how they are going on. After the experimental work has done and got the MATLAB results, I have done the same thing in the ANSYS software. So this is the home page of the ANSYS software. Like there are different types of contents what we have, like materials and everything. So this is the properties of the steel what I have considered, like Young's modulus and Poisson's ratio and the tensile strength, whatever you want you can give to your structure. And after that we have to give the geometry, like length of the beam and height, width, and what are the properties of your geometry. So I already told that in experimental procedure I have selected a C-section beam which is having a length of 750 mm and height of 30 mm and width of 62 mm. So this is the geometry of my C-section beam. So like this I have extruded my structure. So after this, here we are giving a meshing. So the meshing will be of different sizes, like different meshing sizes, like it's average or moderate or fine. So based on our structure, we are giving the meshing. So here I have considered the fine meshing, and after that I have given the boundary conditions. As we know that simply supported beam has the boundary conditions like one end fixed and one other end roller. So I have given a hinged support at one end and a displacement at other end. So I have given a free, so that's why I have done a displacement in z direction and other ends are restrained. So after giving the boundary conditions and everything, so now I so the results what we want, like deformations, anything whatever you want, we can give in the uh, like solving part. And after solving it, I have got these mode shapes. So this is my first mode shape of my structure, having the natural frequency of 195.71 hertz, and second frequency of 16.41 hertz, and third frequency, natural frequency of 1074.6 hertz. So these are the mode shapes what I have obtained from my structure through the ANSYS software. So when so these are the results what I have got, like first one, second and third one. So I have done both the ANSYS and experimental work. So these are the results what I have got from both the works, like experiment and simulation work. I have here the both the results are same. So with a minute error, it's based on the, maybe it's based on the software or like some variations in the force. So it's almost near. So these are this is the conclusion what I have to give here. Whatever the work we have done, either it's experimental or it's simulation work, it almost be same, and we have seeing the both results very close to each other. So thank you very much for giving this, and what I have to conclude is the both the results are almost same, and thank you.